I'm going to jump in here, everyone, and hope that by saying a few sort of traveling music kinds of sentences that will slowly quiet the room and feel good about the next presentation. And maybe some people who are out in the hallway who can't hear this will slowly sneak in, because I'm really, really excited today and honored that Paul Anastas is going to speak to us. And I'll give you the bio, some of which is on the screen. Paul is the Teresa and H. John Hines III Professor in the Practice of Chemistry for the Environment. And he's also director at Yale for the Center for Green Chemistry and Green Engineering at the Yale School of the Environment. And Paul is an entrepreneur who started a lot of companies. He's been a policy advisor and a policymaker in Washington at the EPA. He's got appointments across the university, and he's been an inspiration to me, so I feel very lucky to have him here. And if you'll indulge me a short anecdote, a student of his, a young colleague of mine, at the end of his green chemistry class, walked up to Paul and thanked him. And Paul said, "Hey, yeah, great. What do you think? How you doing?" And the student said, "Actually, I'm not really good." And Paul said, "What?" He said, "Yeah, if I'd had a decent chemistry teacher, or a better one like you in maybe high school or college, I might have been a chemist." And Paul's response was, "Huh, that is a bummer." So it's a testimony to Paul as a teacher as well. He's taught me a lot, and I hope that today you can get a little bit of that incredible experience of hearing Paul talk. Paul, welcome to Yale School of Architecture, and thank you for coming.
Thank you so much. Thank you so much. Alan Organsky is someone who inspires me, both for the fact that he has maximum talent and brilliance and maximum humility. So thank you so much for putting on all of this, shall we? Thank you. It's a very kind introduction. I appreciate that. So I guess a couple things that I ought to say at the beginning to warn all of you. I am a person who views the status quo as somewhere between an absurdity and an obscenity. What I mean by that is that we've been doing things so wrong for so long, we've got nothing but opportunities. And, I ought to set my timer because I can go on and on about this type of thing for quite some time. What I've been told is that Socrates could wax on philosophic for days at a time, and they killed him. So I will try to be brief. When we step back and think, and we often hear today, how did we get to this place? How did we get where we are? How did we get here? And I genuinely believe that we are where we are because we do what we do. And we do what we do because we think like we think. What I want to do today is perhaps show some different ways of thinking, some of the different thinking that we try to bring into the work that we do up at our center, but that people are doing all around the world. So the first disclaimer is that, isn't that a great slide? Let's pause on it because it's just such a great slide. That I am a simple country chemist. And this will actually be a genuine picture of me in 10 or 15 years. So I'm a simple country chemist, and I am here at the School of Architecture talking about regenerative building, but it is one molecule at a time. Now I have to say that when you're a simple country chemist and you find yourself around a bunch of designers, as I did recently at a design party in Manhattan. It's a very, very sophisticated party with lots of fashion designers and others, and I'm at the cocktail party, and people come up. There's a person that came up and said, so, they actually saw, it was a sophisticated soiree, and they sashayed up. They sashayed at the soiree. And they said, so, what do you do? And I said, I'm a chemist. They said, oh. Another one came up and said, what do you do? And I said, I'm a chemist. And they said, oh. And off they go. Finally, a third one comes up and said, what do you do? I said, I'm a molecular designer. And they said, oh, how intriguing. So as I engage in molecular design at this Manhattan soiree, I have to say that there's one thing that that chemists think about a lot. And why is chemistry so important to the discussion that we're having today? Is because while I won't be talking a lot about the raw quantities of materials that are put into this type of building or that, or the flows or the stocks, because we've heard some brilliant talks about that. What we do know is that it's the character and the nature of those materials that's not only critically important in terms of its impact, both positive and negative, but it's also what's most accessible to design. Accessible to design of those materials at the molecular level so that you can change the consequences and the impacts, not only of the performance, but of the adverse impacts as well. We talk about chemical bonds a lot, but we have to recognize that it's because of the strength of the carbon-carbon single bond that we have a petroleum-based economy. It's because of the bond strength of the carbon-carbon double bond that makes it carcinogenic in so many situations. It's the way that the carbon-carbon double bond twists and stretches and vibrates that we have a global climate change problem. And it's the strength, the amazing strength of the carbon-fluorine bond that makes it the basis of forever chemicals that build up in our bodies in the biosphere. So those observances of the impacts means that they're going to cascade not only throughout our society and our economy, but also throughout generations. So yeah, chemists make a lot of stuff. And it's a lot of stuff that's directly central, essential, and crucial to buildings and the practice of building. Whether it's cement, steel, coatings, paints, insulation, you can go on and on. Everything we see, touch, and feel is a chemical. Every material is a chemical. All we have, as everyone knows in this world, is energy and matter. And what green chemistry is all about is how do you redesign the molecular basis of our society and our economy, including all of the materials that we use to generate, store, and transport our energy, in ways that are not going to be harmful to people and the planet. Because at the end of the day, we know that you cannot bake a delicious cake using rotten eggs and spoiled milk. In other words, you can't build a green building with toxic building materials, and you can't build a living building with lethal materials. And so everyone in this room knows the fundamental importance of intention in design. I'd suggest that design without intention is an oxymoron. Some of my favorite oxymorons would include even odds. Ill health, deafening silence, jumbo shrimp, minor miracle, random order, pretty ugly, and of course, accidental design. You can't do accidental design, so thinking about thinking about how we put that intention into the molecular structures of all of the materials that we're going to engage in the building practice. So chemists, what did we actually intend to do? I just said that the status quo is somewhere between an absurdity and an obscenity. Did he say that? I said that. Did I say that we've done things so wrong for so long, we've got nothing but opportunities? Yes. So what was it that we intended to do? What was it that we were striving for in our design frameworks that brought us to where we are? Well, we strove for efficiency. We strove for efficiency and we achieved it. Manufacturing processes and petrochemical refineries are nothing short of a technological miracle. If you look at the efficiency in a petroleum refinery, it is astounding. If you only got 90% efficiency, you would be out of business. Efficiency is something that we achieve. The materials that we relied on, we strive to be predictable, stable, static. Whether you're going to go out of the solar system like Voyager spacecraft or down to the bottom of the Mariana Trench, stable, static, durable, re-entering the Earth's atmosphere, bulletproof vests, whatever it is, we strove to make these things durable. And we wanted to have high purity. We strove to get purity, whether it's in our medicines, our reagents, our electronic systems, and of course, we wanted to have high functional performance, great performance, whether it's on hurricane-resistant houses or insulation or whether, yes, even things to wear at the bottom of the earth to keep yourself alive. That functional performance is nothing short of astounding. Now, what is that we actually achieved in what we produced? We know that the largest product of manufacturing is CO2. I didn't say desirable product. I didn't say commercial product. I said the largest thing that we produce is CO2. What we produce is changing the only climate we have, and it's changing it for centuries. And if we take a look at the materials that we use, that we produce intentionally, we're going to have over a megaton of fish in the ocean by 2050, and we're going to have over a megaton of plastics in the ocean by 2050 as well. I could go on, but I'm not into being a bummer. The truth is that much of our traditional chemistry is not conducive to life, and it needs to change. If I said that the power and the potential of chemistry to cascade through our society and our economy is there, and it has done it in both a positive and negative way, then what the challenge is all about is how do we do it in a way that maintains all of those positive benefits without all of the negatives that we've experienced over and over again. Friends of mine up in Northern Ireland sent me this story. May or may not be true, but it's a good story, where it seems as though there was a little accident and a van wound up tumbling into the harbor. And they needed to get that little minivan out of the harbor, so they brought in the crane. And luckily, nobody was hurt. They were able to get the minivan lifted, but oh no, the crane falls in. All right, so this is a can-do audience. What do you do when that happens? What's the solution? Bigger crane, that's what, a bigger crane. Now that's what we call a crane. Yeah. What could go wrong? As Einstein says it best, insanity is doing the same things over and over again and expecting a different result. So we talked about how we got this wonderful prize of efficiency, purity, durability, stability. All right, here's the uncomfortable part. Here's the elephant in the room. Is it possible that the exact things that we were striving for, the exact things that have been the pillar of our design framework that we were trying to achieve, that brought us all of these success and achievements, are the same things that are contributing to our demise. Well, I'll say at least we can all agree on one thing. We can all agree that efficiency is a good thing, right? Let's see a show of hands. We agree that efficiency is a good thing? All right, the vast majority say yes, efficiency is a good thing. Yeah, I'm here to tell you that efficiency has no value, that efficiency has no nobility. There are several of my engineering friends in the audience who are visibly twitching right now. Oh my goodness. So, all right, so you want me to prove it? You want me to prove it? I'll prove it. How many people would want to have an efficient mass murderer? Oh, okay, nobody. How many people would want to have a very efficient, aspiring dictator trying to consolidate power? No one. How many people would want to have an efficient toxic substance? No one. How many people would want to have an efficient virus? No one. So what's my point? It's not a trivial point, because we know that the value of something doesn't come from how efficient it is. It comes from the action itself. If the action is good, if it's noble, if it's constructive, then you want it to be more efficient. And if it's not, then of course you don't want it to be efficient, right? Why do I mention this? It's because we have spent probably the most of my lifetime with people trying to make fundamentally unsustainable products, processes, and systems more and more efficient. It might make them more socially acceptable, might make them in compliance with regulations, but it's not going to transform something that's unsustainable into something that's sustainable. Efficiency might help you do the thing you're doing better. It's not going to help you do a better thing. And of course, one thing we know for certain, when we're talking about sustainability and efficiency, there is absolutely nothing about sustainability, about nature itself, that requires efficiency. Virtually every process we can name in nature and biology and physiology, ecosystems, is tremendously materially and energy inefficient, right? So, yeah, that whole efficiency thing, that pillar might have to go. Stable, static, resistant to change. Remember, we were aspiring, striving toward that. Yeah. I don't need to tell this group that success, that ability of brilliant chemists over the past 100 years to get things that were static, stable, durable, and long-lasting has got us this, has got us PFAS, has got us the forever chemicals that are building up in our bodies in the biosphere. And I don't think any one of you ever signed a waiver saying, yeah, I don't mind if you have build up synthetic chemicals into my body. No, don't think you did. So you really only want to design things so that they last as long as you want them to and not a minute longer. So yes, design for degradation is really important. That whole thing about purity. We've got a challenge when it comes to purity because there's absolutely nothing in nature that's pure. Slight exaggeration, you might find a diamond that if you make it small enough, it's kind of pure. But the fact of the matter is, nature gets all of its performance from very complex mixtures. Complex mixtures are something that we do not know how to do. We don't do mixtures very well. We know how to control things, make things pure, and manipulate them for our purposes, sometimes torturing them until they're torturing our materials until they scream and do as we wish. So we need to evolve from pursuing purity to be able to master mixtures. What was the next pillar? Function. Come on, that's our holy grail. We're so proud of achieving function. You know, the problem with CFCs was not that they didn't function well. They did what they were supposed to do really well. The things that came before them burst into flames and were poisonous and all kinds of nasty stuff. CFCs, they function fabulous as refrigerants, so many applications. The fact that they, were destroying our ozone layer, yeah, that was a shame. PFAS, the problem is not that it doesn't function well. Oh, it functions fabulously, whether it's on clothing or non-stick cookware or in electronics, it functions fabulously. The fact that it persists and has a litany of toxicological consequences, it's not that it didn't function. PVC is used in so many applications, certainly in building, but in so many other applications as well. It's not that it didn't function, it's that it has potent carcinogens at the beginning of its life cycle. Upon most disposal via incineration, it has even more toxic byproducts like dioxins. It's not that it didn't function, it's that the adverse consequences were a problem. So what does that wind up meaning? That we need to redefine performance. The materials that we're going to be making, instead of just functional performance, it's function divided by hazard. You want to have that numerator go to infinity. You want that denominator to go to zero, for that ratio to go to near infinity, because we want to preserve that function while trying to minimize that hazard. How do we get here? Reductionism, as folks in this room know very well, has allowed us over the past 200 years to understand the universe in ways that we never would have thought possible. Reductionism, taking all different parameters, all different factors, holding them all steady, while changing just one and observing how that changes the system, reducing things down, breaking them apart, analyzing them so that we come to understand the world. And we can make the world predictable, and we can make the world understandable. Reductionism has allowed us to have insight into the world in so many ways. So why do I mention this? Because you can't drive this car. Reductionism is wonderful. It allows you to know what role the carburetor plays. It allows you to know where the fuel injector sits in the overall system, but you can't drive this car. Why? Because it is a complex, integrated system that if you are going to actually drive that car, you don't need to just know the parts. You don't need to just know the pieces deeply. You need to understand the interconnections. One of the best papers that I ever read in my life was by the great Nobel laureate physicist P.W. Anderson. Back in 1972, Professor Anderson started this paper, More is Different, by saying the reductionist hypothesis may still be a topic of controversy among philosophers, but among the great majority of active scientists, I believe it is accepted without question. That was 1972, and in 2025, I'm going to agree with Professor Anderson today. I believe that it is still largely accepted without question. But perhaps the most important sentence in this whole paper was that the main fallacy in this kind of thinking is that the reductionist hypothesis and by no means implies a constructionist one. The ability to reduce everything to simple fundamental laws does not imply the ability to start from those laws and reconstruct the universe. So why would I take your time in putting up this paper? Because most of what we have invented, most of what we have, quote unquote, designed, has been by using reductionism. And most of the performance that we have gotten has been as a wonderful product of this approach, and most of the unintended consequences, most of the adverse challenges that we are facing today, whether it's energy, water, material flows, are also due to the fact that we are not understanding and integrating in those interconnections. So when we think about the challenge of building and shifting from integrative systems thinking that complements, not replaces, complements reductionist thinking, how would this influence what we build? How would it influence how we go about building it? How would it influence how we experience what we build? And what would happen if we could actually understand these interconnections so that, yes, we got the positive consequences without all of the adverse consequences. One of my favorite ancient sayings is, you think you understand two because 1 and 1 is 2. But first you need to understand and. To a first approximation, we're not very good at understanding and it might be the most important word in the dictionary. So, when we think about what we have strived for previously and what I would suggest we may want to consider evolving to, this is a different design framework and a different way of thinking about what we design is something that, again, has impacts throughout not only what we do and how we do it, but how we think about it. So, as our design thinking evolves, what does this wind up making possible? Because if we turn to say, well, what in the world is a model for this kind of thinking? What can we look to as a mentor? It's not shocking. It's not shocking that I would say that nature is the best chemist in the world, period, full stop. If chemist were a human being, she would be winning every Nobel Prize in chemistry for the rest of eternity. Anytime we try to compare ourselves to nature, we embarrass ourselves. So when we take a look at that 3.8 billion years of experience, I will say that there are times when I listen to some of my dear, beloved chemistry colleagues, and they talk about what they are able to create, and there's this new phrase, a new-to-nature chemistry. This chemistry is new to nature. I think we're supposed to smile and applaud. I'm not sure, but I will tell you that I had dinner with one a few months ago up in Stockholm, and she was saying, yes, we've created this new-to-nature chemistry. And I said, nature had 3.8 billion years to try out every chemical reaction, make every product that it wanted to. If it decided not to, if you say that you revere nature, that you love nature, that you respect nature, will you just pause and think, why didn't she keep on doing it, you know? Because when we're making these novel amino acids, things like PFOA, PFOS, et cetera, it's worth pausing. And instead of saying, oh, we can better nature, it's more rational to say, okay, maybe nature decides against it because nature actually making sure it's conducive to life. We don't seem to put that constraint on ourselves. Now, what is possible when you start looking at what nature does and how it does it? Instead of having static, stable, durable, you start thinking about dynamic, adaptable, changeable systems. So instead of asking, gee, what color what color is your house? You say, what color would you like it to be? Instead of saying, for instance, oh, is this material going to absorb water or is it going to repel water? What would you like it to do? Is this a conductor or a resistor? Well, which would you like? The ability for materials to change upon imparted stimulus, rather than us saying, oh, this material does X and this material does Y. And if you want a material that does such and such, no. Can we design materials such that they change their behavior upon stimulus? Yes, we can. This idea of wanting to make sure that things stay solid, durable, static, right up until they don't. The design challenge is simply, how do we look at what stimulus, whether it's pH, whether it's a certain wavelength of light, whatever it might be, that it's not going to encounter during its useful life. And when you want it to degrade on command, you expose it to that particular stimulus. This is just a particular example of degradation on command. But I will say it's a particularly important example because when we talk about circularity, I think all of us would agree that circularity is nothing short of a near miraculous concept that of course we should be emulating, and our current material economy is nowhere ready for it. What I mean by that is if we take a look at the current material economy with all of its toxicity, with all of the flaws that I've been naming off, and we want to lock that into cycles, that is not wise. Have we designed our material economy to be designed for disassembly? No, we have not. Does that mean it's going to take an incredible amount of energy, an astounding amount of energy in order to do the separations necessary in order to even achieve that circularity if it were desirable? Yes, it would take such a quantity of energy to do that separation that it would most likely offset any advantages that we got. So does that mean, Paul, you're saying abandon circularity? No. What I'm saying is design for circularity, design for disassembly. It is absolutely what we should be aspiring to, but we have to build that design process into the discussion. Yes, feedstocks that are renewable, plentiful, and from waste. And of course, we've talked a lot about wood, but I will tell you we have to stop treating wood as dumb lumber. Wood is brilliant. Wood is so amazingly complex, and we do not give it its due. We are thoughtless when we do not give wood the respect it deserves. It's not just that it doesn't work as a computer, it just works better as a paperweight. The idea that we would treat wood with such disrespect when its elegance and what its power and potential is. This is something that we've done recently in our lab, where we're going directly from wood to new polymeric materials that have a wide range of performance characteristics that are designable, customizable, and yes, of course, not only renewable, but degradable on command. So this idea that we can only, use lumber in a limited number of ways, use wood, I should say, in a limited number of ways, I think is selling it short. We know that lignin, the structural basis of wood and so many other woody plants, is our only natural source of so-called aromatic chemicals, those cyclic chemicals that are crucial in our economy. Crucial, you say, Paul? Yes, crucial. Those aromatic chemicals are the reasons that when they're in fuels, they're the reason that planes don't fall out of the sky. They are crucial chemicals. And this little catalyst was able to transform lignin into many valuable specialty chemicals. Well, why is that a big deal? Well, because for decades, the idea was, well, don't bother with lignin. It is too hard to change. It's not going to go anywhere. It is so stable, not going to happen. Don't bother with it. That's why 98% of it is burned. Yeah, 98% of it is burned. This is now the basis of a couple companies, and it's all about taking advantage of how we learn nature's chemistry combined with new catalytic processes. So just standing back and look at the elegance of wood and taking advantage of that structure in order to emulate it in self-healing materials. Self-healing materials mimicking the way that wood works, combining it with catalysts that we're able to design, creating self-healing systems. Taking a look at not just wood, but other biological systems that nature has, certainly how we heal, how we clot through oxidative processes allows us to make new materials that, once again, instead of worrying about durability and last forever, it's no, how do you heal when those types of problems take place? Even derivatized wood, there's some wonderful work going on across Yale of taking the molecular structure of wood and modifying it so you can design and customize it in order to take advantage of its natural strength and structure. So I would ask that if we have this conversation about how to emulate nature, and we told them to bring all of their best science and engineering to the challenge of trying to redesign a bird, do we think that it would fly using our usual reductionist approaches? I'm going to suggest no. Until we start taking nature as the mentor, design partner, looking at things like the beak of the toucan, the way that it's not only its shape, but the way that it fills and lightweights the materials. This is true across the toucan beak, but it's also able to be mimicked with things like titanium and aluminum, that you get superior strength with lighter weight, as many of you in this room know quite well. So whether it's how we obtain strength by mimicking nature, or using, in this case, I have a personal affection for horseshoe crabs, taking this cross-section and using this as a way to mimic the structure. So this is just some of the structural, what would I call it, structural motivations, structural examples, but it's also how we use nature to inform the processes. Local renewable resources, using weak bonds, subtle weak bonds, hydrogen bonds, which are the reason why water, which has no business being a liquid, but because of these hydrogen bonds, is a liquid that expands upon freezing, otherwise known as why life itself is possible. Using these weak bonds, weak force interactions, low energy input, catalytic, in order to get performance. We need to build those types of things into our building frameworks. So I'll ask, can you grow a building? Well, perhaps not yet, but maybe you can grow some of the materials. maybe we can let our imagination run wild and say, this could be amazing if we could, instead of carving and etching, we could grow things. We could use molecular self-assembly that nature does so well. How many folks have been to Giant's Causeway in Northern Ireland? Any folks? Okay. Is it amazing? It's amazing. So this is Giant's Causeway. These have grown here naturally, right? And if you start saying, oh wow, if you can grow things like this, then maybe you can make a house that looks like this. This is not real. This is not real, okay? But you can imagine using Giant's Causeway and say, but hold it, Paul, those took forever to grow. That took a long time. Remember when I said catalysis makes things go really fast? Not just thousands of times faster, hundreds of thousands of times faster, millions of times faster. One of the things that we can do when we're working with nature is saying, okay, you showed us the roadmap of what can be done. Maybe we can make it go faster. This is a crystal of bismuth. I don't know about anybody else, but I find this to be beautiful. The bismuth house. This is not real. Okay, this is not, but understanding the growth, the molecular forces, is the type of thing that can inspire us and inform what is possible. The idea of molecular and material self-assembly, and of course, one of the things that we always want to do is not just work in 3 dimensions, but maybe the 4th. Let's see if we can make this work. My friend Dave, can we make this work? Just going to say that Amazon is really interested in speeding that up, right? Can you imagine? Imagine IKEA saying, throw away your hex wrenches. We will assemble your furniture all by itself. But yes, if we can do it at a larger scale, that's my next condo. So go on from that. So molecular self-assembly is something that is just at the cusp of exploring what's possible, but it's the same intermolecular forces, this same self-assembly that does things like forms bone. So let's see. I know that most ceramics, most of our hard high-tech ceramics, are heated at 3,000 degrees for 50 hours in an oven. These ones that we talked about on space shuttles and shields and things like that. Yeah. How many people in the audience have bones? Okay, yeah, I do too. Okay, and I don't know about you, but my bones are pretty hard. How many people have been baked in an oven for 3,000 degrees for 50 hours? Yeah, none, right? And so what's the point? The point is, this idea of molecular self-assembly, in order to get all of the functional performance, superior functional performance, without all of that, yes, energy, heat, and the accompanying environmental impact is something that nature does in her sleep. And it's because of the molecular structure that, yes, chemists understand extremely well. This is not that we don't understand it. It's that we've never had as a performance criterion considering these things. Chemists, I'd say generally, material scientists generally, have met the challenges that have been put to them, have addressed the problem statements. And what we did was we got the problem statement wrong. Getting the problem statement right is where all of the potential lies. So whether it's cork or balsa or cuttlefish or iris leaf, we see these structures over and over again, brilliant structures. And yes, we've all seen how they've been taken advantage of to some degree, because this is the deep sea sponge, and we all recognize some of these iconic buildings and architectural forms. I'm going to finish with a paper that recently came out of the Center for Green Chemistry and Green Engineering. And this is known as the CO2 tree. The CO2 tree uses this metaphor to show that all of the different things that you can convert carbon dioxide into. I can tell you that when I was sitting in university, I was told that converting CO2 into anything useful was a fool's errand because it was at too low of an energy state. The idea of converting it into anything useful or commercially viable was quite foolish. This is now a review of over 300 examples of all of these different platform chemicals, basic chemicals that, when we harken back to the beginning of this talk of all of the things that are relevant to building that chemists make, can be found somewhere in this tree. Changing our greatest problem into one of our greatest opportunities is what I hope future generations will look back on this time as doing. How we transform CO2 into, yes, the basis of some of our most high performance building materials while sequestering tremendous amounts of CO2. Doing it in a way that increases the performance of our building materials to the point where, when we talk about rapid urbanization and we wring our hands about how much CO2 is going to therefore need to be evolved into the air because we're using today's technology, we instead say, oh, thank goodness, because it is sequestering so much of this CO2, and we have an incentive to capture and utilize and fix all of the CO2. Build, baby, build. I'm kind of kidding about that, but but what I'm not kidding about is I started off by talking that we do what we do because we think how we think. Bringing a different perspective to how we design and what our design frameworks are, what our design goals are absolutely crucial. Nature does this in her sleep. This is just from Oman, the fixation of CO2 that has been going on for millennia. Fall back to my recent comments about catalysis speeding up this process, because this is what fine and feathery cement looks like. This is what it looks like after it's sequestered so very much CO2. And I just want to give one last example. When we start thinking about all of the great grand challenges of energy and how our energy is generating so much CO2 currently, then I'll give this a try.
Time to take off. To take off the limitations of how fuel is made. To take fossil fuels off the table. And take on the responsibility of sustainable innovation. It's time for a new take on takeoff. Introducing a jet fuel made from the very air we travel through. We're using carbon technology to take CO2 from the atmosphere and transform it into sustainable aviation fuel, turning our planet's most abundant pollutant into a never-ending resource. The path to a cleaner future is in the air. Time to take off.
I'm proud to be affiliated with this technology. The idea of going carbon neutral, turning our CO2 into sustainable aviation fuels, the idea of having guilt-free travel for one thing. It would be nice. We're doing this with the Air Force and with NASA. And when you talk about, oh, is this all theoretical? When you see this fuel being pumped into an Air Force jet and the jet streaking down the runway and then going across the sky, that becomes very real, very fast. Scale up is taking place up in near Niagara Falls. I just want to finish by saying the question used to be, 30 years ago, the question used to be, can we actually design the material basis of our society and our economy so that it's genuinely sustainable, that we get the performance without all of the adverse consequence? That question has been asked and answered. The answer is yes. Yes, we can. Now the question is, will we? We have shown how to take the so-called impossible to the possible into the practical. Now we need the same kind of innovation from business, financiers, venture capital, in order to turn that possible into the profitable. The difference between what we do and what we are capable of doing is more than enough to solve most of the world's problems. It's been an honor speaking with you tonight. Thank you. Thank you.
I think we have time for a few questions. I have many, but I know the audience has been shortchanged today, so instead I'm going to capture the vibe you've set up here, Paul. And Charlotte and Max have mics. The reason we're using mics is because we want to record everything everyone says and incorporate it into hopefully a book, including audience questions. So I'm going to start with Ava, and Max, you have the mic.
Thank you. Hi. That was a great throwback to being back at school, and inspiring as always. Really simple, practical question. Yeah. I am wondering about the timeline on the commercialization of the aviation fuel, because obviously want to travel guilt-free as soon as possible.
Well, agreed. So it's no shock that the reason that the first two giant clients are the Air Force and NASA is because they're willing to pay a premium. The ability to go to a larger scale will follow that initial volume, and the more volume you get, the lower it's going to go, and the more capital that's going to flow. So will large-scale production be taking place in Niagara Falls in the next 3 years? Yes.
Any other questions? Yes. Thanks, Scott, for waiting.
I will say really quickly, one of the things that we have seen over and over again, whether it's the projections on solar proliferation, projections on battery life, projections over and over, is that the projections are far slower than we actually realize. So things have a way of going faster when people recognize, we should have been doing this all along. Yes, please.
Chemistry was my least favorite topic, I think, in high school. And this is my favorite talk. It was amazing. So thank you.
Thank you.
I'm thinking from educational point of view for architects and designers. Would you, going to the systems thinking piece, which you presented so beautifully, and now I think it's really entered the discourse of architecture and design fairly recently, strangely that it's taken this long to be there, but combining those two things, what could we be adding to curriculum in architecture and engineering programs to really help build the deep base of skill and knowledge with these concepts? Because I think we're still so stuck in an analytical and disassembly mindset. And so I don't know if your background has merged with architecture to the point where you've actually engaged with that specifically. Anything you want to share about that for the professors?
I'd love to. First of all, thank you. whenever introducing any of this, I think, especially to students, I think that relevance is absolutely key. So I'm lucky enough to teach a sustainable product design course with Professor Zimmerman. And one of the things that we see is whether there are engineers or architects or, quite frankly, business folks or environment folks, what they want to see is how the old way has its flaws and this new way is going to provide a different perspective on how to do things better. And so making that systems perspective show how you can do things that you couldn't do and think in ways that you haven't been able to think before, all of a sudden that gets folks quite excited about exploring that. So, yeah, thank you.
You very astutely said that we can't lock the damaged products in with the circular economy. So to that end, how must we also design our products that can be designed for decomposition of what currently exists in a way that is not harmful to our new world order, for lack of a better term?
Oh my goodness. Well, I don't know how to give a short answer to this. I'll try with an example. We recently, 3 weeks ago, just got a provisional patent on how to take waste polyethylene, the largest polymer made, the largest plastic, take that waste polyethylene, break it down, combine it with CO2, so putting molecules of CO2 into making a new plastic polymer that has properties similar or identical to the original polyethylene. So you took this, one of our largest waste problems, and turned it into a desirable, renewable, degradable product. Now I said waste polyethylene. Does it have to be waste polyethylene? Going to break it down into polyethylene. Why wouldn't it be possible to just use the same old ethylene that starts at the beginning, insert that CO2 at the through the process, and all of a sudden our next generations of now polyethylene are going to be polyethylene esters which break down naturally. So is there a way to both design up front, also to retrofit, also to deal with existing legacy problems? There are ways to do that. It's really just simply a challenge of thoughtful design.
Hi, thank you for the talk. You just mentioned patents, and so it made me think about the context of knowledge sharing in this new world that we've all been talking about today. And it's particularly challenging in different countries to a certain extent, but in the US, patents have so much influence, but then when you want them to have a lot of power, sometimes they have no power. What do you think about the future of patents and their role in driving forward this future?
So I would like to have control over the patents so I can give them away, rather than have somebody else capture them and bury them. So for instance, we have a very large program in Africa called the African Power Initiative. And that is able to, it's too long to describe, but we were able to take nutshells and nut oils using the integrated biorefinery to create many different businesses, provide biofuels, deal with soil health, and on and on and on. Now, do we have patents on many of those processes? Yes. Do we give them away freely? Yes. So I think that's what's interesting is I think that I would love for all of this IP to be freely available, but I also want it to go to scale. So I often say, if the world, imagine $1 trillion technology, maybe it's an energy technology. If $1 trillion technology makes $1 billion each for 1,000 people, that technology is going to happen. If that technology gives $1,000 worth of value to 1 billion people, that technology is probably not going to happen. Why? Because nobody's going to invest in order to bring that to scale. What if the world actually needs that technology that brings $1,000 worth of value to 1 billion people? So I want things to go to scale. I want things to have as much benefit to as many people as possible. While I think the rules of the game are fundamentally flawed, I want to, let me emphasize that, fundamentally flawed. But I just want things to go to scale as quickly as possible for as much benefit as possible.
We have, unfortunately, time for only one more question, and I think you were about to ask it, so I'm going to...
Yeah, okay, thank you.
Hello.
Thank you for the presentation. There was a lot to talk about. It was really enjoyed it in so many levels. But you did land in a very important, I think, note that I'd like to touch on. So the industrialization process, except of having, we're seeing all the impact that it has on ecology, but also in human health. And this idea to shift into designing at a molecular level and creating materials that are biocompatible and biodegradable and self-growing houses, as you mentioned. I think that the industrialization process, besides having created this huge crisis of which is the climate, it's interlinked with a lot of other crises that we are experiencing. And one of them, it is the loss of culture generally. So my question is, if we would shift from one, let's say, manufacturing process into a different one, which is designing at a molecular level, we are still creating an avenue that drives us again to loss of culture and our ability as people to create and craft. Because, it seems like, and I don't even want to get into the implications of, self-replicating molecular molecules, I guess.
So just to be clear, the molecules I'm describing aren't living and they won't self-replicate. They'll self-assemble, but they won't take over the world.
Yeah.
There you go. So it's, I do think that moving from the way that we've done things to doing chemistry and molecules and materials that are conducive to life rather than harmful to life, I do think that that's a positive step forward. I promise I'm not trying to sell books. We just did a book called First Do No Harm, and it's about the basics of how you do it so that it's not going to cause harm either for humans, the biosphere, the biogeochemical cycle. So that's sort of a roadmap. How it impacts culture more than in a negative way versus how we are doing things today, maybe it's a long conversation over wine. I don't know.
Very nice wine, a beautifully crafted wine. Yeah. I want to thank you again, Paul, for this really great.